Hi, good morning once again. This morning we'll be seeing and we'll be talking about nodal analysis. So this is just like a brief introduction to nodal analysis, and this is under circuit theory for 300 level students. All right. What is nodal analysis? Is just a circuit analysis method where you actually look for unknown voltages or node voltages. So that's briefly what nodal analysis is, and that is what it's all about. So for nodal analysis, you are looking for unknown voltages at the node. So what is a node, if you might ask? A node is simply a junction where two or more circuit elements meet or are connected, right? So this is a current source, it's a circuit element. This is a resistor, it's a circuit element. And by the way, you can see that the resistors here are labeled or are given, the values of the resistors are given in Siemens, right? That's the conductance you are given instead of their resistance. So this is 1 Siemens, this is 0.5 Siemens, and this is 2 Siemens. And remember, the conductance in Siemens G is equal to 1 all over the resistance. So in case you missed that, that is it. So this is given the circuit, the resistance is given in Siemens instead of the usual ohm. So whichever we were given, we can work with that. So whether our resistance is given in ohms or in Siemens, we could work with that. So back to my question, what is a node? A node is just a point where two or more circuit elements join. So for instance, this is a current source, this is a resistor, this is a resistor. They join at this point, so they form a node here. So you have a node. I'll call that node. Let me call that let's say V2 for now. Then node V2. Then here is another node, right? And then I'll call that node V1. So these are two nodes from the circuit. So because why is this a node? Because this element here, circuit element, which is a current source, joins with a resistor and another resistor. This is the junction where they meet or join. So that makes this place a node. How about this point? One might ask, well, this is not clearly a node. It's actually a node, but then it's a trivial one in the sense that you can actually itemize this place to be the junction where resistor join with any other thing. This is just some piece of wires, if you can see. But then if you take the whole of this together, the whole of this lower part of the circuit together, because this resistor joins here, the current source joins here, the resistor joins, so this is just like a bar or a conductor that joins all of them. So if you take all of them together, you can consider them to be a node. So this is also a node. However, this very node is called a reference or ground node. It's called a reference node because it has more elements connected to it. For instance, this node here has 1, 2, 3 elements alone connected to it. This node here has 1, 2, 3 elements connected to it, whereas this very node, this lower part of the node, because I told you the whole of this is a node, so this lower part has 1, 2, 3, 4. This is the fourth element. So 1, 2, 3, 4 elements all joined together. So the node with the highest number of elements connected to it is called the reference node. And reference node are usually denoted by symbols like this, right? So this symbol tells you that this is a reference node. And for most of the time, you give the voltage at the reference node, you give it a value of 0 volt or ground voltage. So that's why this node, to some extent, is called the ground most of the time. If you're an electronic student, you must have come across this symbol. This symbol represents ground or earth. So this is a ground node, and the voltage at the ground node, as being a reference, is always taken as 0 volts, right? So these two other nodes are usually the problems that were. So for this case, let's just formulate a question from this. Find the node voltage, the node voltage V1 and V2 using nodal analysis, right? Using nodal analysis. All right, so we have to find the node voltage V1 and V2 using nodal analysis, the solution to that. And sorry, before I proceed, okay, maybe during my the case of explaining, I will just chip that in, right? So for us to use nodal analysis, we will always apply our Kirchhoff's current law, KCL, to each of the nodes, with the exception of the ground node. So we are applying KCL to node 1 and node 2, but would not apply to the ground node because there is no unknown voltage on the ground node. The ground node voltage is known, which is 0 volts, right? So it's known, so there will be no need of applying KCL at that node. So apply KCL at node 1. Node 1 would get from node 1 here, you apply KCL at it. You talk of current entering and current leaving. Now, if there is a voltage drop across the resistance, you will know that there will be a current passing through it. Now, this is what I want you to pay attention or take note of. If, for instance, I'm concerned about the current flowing out of this node, right? If current is flowing out of this node, then here has to be the positive terminal, here has to be the negative terminal if current has to flow this way, isn't it? Similarly, if current has to flow this way, from node V1 to node V2, then I will here have to consider here to be, for now, the positive and here to be the negative terminal. Now, I don't want to write this in bold because when I consider for node 2, the situation might change. But then let me just maintain that here is the positive and here is the negative terminal with a current flowing like this, right? All right. So if you have a current in this direction, you might want to ask yourself, what's the value of this current in this direction? Now, the current in this direction is simply nothing but, if you have, this is just an example, please. This is not part of the solution. Remember, this is node V1 and this is node V2, and then we are looking for current in this direction. Let's say this is conductance 0.5 Siemens. So if you are looking for that, you get your current I to be equal to V1 minus V2 multiplied by the conductance 0.5 Siemens. All right, so that's the current in this very branch. So apply KCL. This is just like an illustration. This is not part of the main thing. So apply KCL at node 1. We know that a current is leaving this way, and then when a current is leaving, that current is usually giving a negative value. So there will be current leaving from this branch across these two Siemens resistor, and that current is going to be the voltage as the positive side minus voltage as the negative side multiplied by the conductance. If it's a resistance, is going to be divided by the resistance. So from here you get that current to be minus because it's leaving the node, and that will be voltage at the positive side, which is V1 minus, this is the positive side, and then voltage at the negative side, that is traced to 0. So it's V1 minus 0 multiplied by this conductance 2, right? So that's this current leaving here. And how about the current entering? The current entering is taken as positive, and the value of that current is 5 ampere. So that's 5 ampere is entering this node. Then how about the other current leaving? Because you have to consider each branch current either leaving or entering. So if this is leaving, you need give it a negative sign, and then that would be V1, that's the voltage as a positive terminal minus the voltage as negative terminal. That's V1 minus V2 multiplied by the conductance, which is 0.5. And then after you are done, you equate everything to 0. This is a statement of Kirchhoff's current law. So you simplify this expression, you get minus 2V1 plus 5 minus 0.5 V1 plus 0.5 V2 equals 0. Simplify this further, you get minus 2.5 V1 plus 0.5 V2 is equal to, take 5 to the other side, minus 5. Call this equation 1. So we are done with the first node. We move to the next node and write the KCL equation or current law for this node, for this second node. So for this second node, we do the same thing we did for the first node. So we are considering for node 2. Remember, the first one was for node 1, right? This is for node 1. For node 1. So for node 2, we would have current entering minus 3 ampere is entering, then V1, if you have V1 and then ground, you have this to be the positive side and this is the negative side. That means current is leaving through this place, right? Current is leaving through from V1 to ground, and then current, already we've established that a current was flowing from V1 to V2 initially. So we take that into consideration. Current leaving by KCL, we know that current leaving a node is this algebraic sum of current entering a node is equal to 0, where we give signs to the current entering to be positive and then the current leaving to be negative. So minus 3 is entering, so it's going to be plus minus 3 ampere. Then that would be this very current, this very current, plus because it's entering, you have plus minus 3 ampere, plus because it's entering minus 3 ampere because that's the value of the current entering. Then how about this current, this very one in this one Siemens resistance branch? It is leaving, so we'll give it a negative sign, and the voltage drop across that resistor is going to be V1 minus 0 multiplied by 1, right? So that would be this current, and it has a negative sign. Know why it has a negative sign? Because that current is leaving the node. Sorry, it is V2, not V1. V2, that's the voltage here minus the voltage here, which is V2 minus the voltage here, which is ground, 0, divided multiplied by the conductance. Then the next is this current. It's also entering, so you give it a positive sign, and the value of that current is the voltage as a positive minus the voltage as negative multiplied by the conductance, which is V1 minus V2 multiplied by 0.5. When you're done, you equate this to 0, right? So from here, we'll simplify this expression. Plus minus 3 gives minus 3. Then if you open up this bracket, you have minus V2, then plus 0.5 times V1, you get plus 0.5 V1, then 0.5 times minus V2, you get minus 0.5 V2. Everything equates to 0. So we rearrange this equation, bringing V1 first, you have 0.5 V1, then minus V2 minus 0.5 V2, you get minus 1.5 V2. Then take this to the other side, you end up with plus 3, because it's crossing the sign of equality, you have plus 3, right? So this could be, let me just remove this plus, just 3, this equation 2, right? So in matrix form, you can write equation 1 and 2 in matrix form. That's minus 2.5, then 0.5, then here is 0.5 and minus 1.5, right, in matrix form. Or you could use any other form or any method of solving simultaneous equation to get your answers. But then usually in electrical engineering, matrix method is usually preferred. So you have this, if you put the two equations in matrix form, you end up with this